of scientific notation, and then do some examples of converting numbers to scientific notation and from scientific notation. In universal gravitation, you have to do a lot of things in scientific notation, so I figured it was a good time to actually review this. So first, scientific notation is used to simplify very large and very small numbers. So very large and very small numbers. So these are numbers that would be really annoying to have to write. So for example, the mass of the Earth. The mass of the Earth is 6 with all of these zeros after it. You would not want to write this number down every single time you use it. So instead, we use scientific notation, which simplifies it to 6 times 10 to the 24 kilograms. So used to simplify very large numbers. The Earth is 146 million kilometers from the sun. And so again, this number is a little annoying to have to write, so we write it in scientific notation. 1.46 times 10 to the 8 kilometers from the sun. So we can also look at a very small number, the mass of an electron. You would not want to have to write this number down and actually like count out all of those zeros and make sure they're all there and then put all those zeros in your calculator. That would be crazy. So instead, you change this number into scientific notation. So simplifies very small numbers. So mass of an electron, I don't even know how to say that without just going 0, 0, 0, 0, 0 forever. Or we could write it as 9.11 times 10 to the negative 31 kilograms. So much more simplified. So now let's talk about how you convert these numbers to scientific notation. So the first thing you have to do is move the decimal. So whether there's an actual decimal or an implied decimal, but you move the decimal so there is only one non-zero digit to the left. Then you count the number of places it was moved. So for example, we have 3 million kilograms. So you have an implied decimal at the end, and we're going to jump it 1, 2, 3, 4, 5, 6 places, so that now instead of 3 million, it's 3.0 or 3. You do not need all of these zeros on the end. That's just showing you how it was jumped over to that point. You can just use 3. And we need to make sure we keep a note that the decimal was moved 6 places to the left, because 3 million and 3 are two completely different numbers. So if we had a decimal now, so a very small number, our decimal spot is now actually given to us, and we're going to jump this one until it has one non-zero. 1, 2, 3, 4. So we have to have that 3 in front of the decimal. And the decimal was moved 4 places to the right. Now, how are we going to use these two numbers, this 6 and 4? Well, now you write that new number, write the new number multiplied by 10 to an exponent, and the exponent is the number of places you moved it. So in our example of 3 million, we moved it 6 places to the left. So if you move the decimal to the left, the exponent will be positive. So it would be 3 times 10 to the 6th kilograms. 3 million and 3 are completely different numbers. If you owed someone $3 million and you gave them $3, they would not be very happy with you at all. So you've got to make sure you include the 10 and the exponent. It's extremely important. So if you move the decimal to the right, like in our other example, then the exponent will be negative. So we move this 4 places to the right, so it's 3.45 times 10 to the negative 4 kilograms. So the reason why that positive and negative is extremely important, well here, this number is much larger than 3, so you need to make 3 bigger. when it's expanded, so it has to be positive. Positive exponents are big numbers. Here, 3.45 is much smaller, or sorry, is much bigger than our original number, so we need to make sure that this larger number becomes a smaller number. The way we do that is with negative exponents. Negative exponents make things smaller. All right, so let's do some practice, and then we'll talk about going the other direction. So 300 million meters per second. So we have an implied decimal spot at the end here, and so we need to jump it 1, 2, 3, 4, 5, 6, 7, 8 places to the left. So now we take our number, which is now 3, and we multiply it by 10 to the exponent. And the exponent is the number of places we moved it. We moved it 8 places. Since 3 is smaller than 300 million, then it's going to be a positive exponent so that this would expand out into a larger number. All right, so 0.00345 watts. And so here's our decimal spot. So we're going to move our decimal 1, 2, 3 places to the left. So we have 3.45 times 10, and we moved it 3 places. And since we went to the right, making this number bigger, we have to give it a negative exponent, watts. 987,000 degrees Fahrenheit. We have an implied decimal spot here. We're going to go 1, 2, 3, 4, 5, and have 9.87 times 10 to the positive 5 degrees Fahrenheit. And then lastly, here's our decimal spot. 1, 2, 3, 4, 5, 6, 7. So 4.3 times 10 to the negative 7 meters per second. So now let's talk about how to convert it backwards. So let's say you have a number in scientific notation and you want to put it into expanded form. So if the exponent is positive, you're going to do the opposite of what you did to create the scientific notation. So if it's positive, you're going to move the decimal to the right. Any spaces that don't have a number will become zeros. So here, our decimal spot is here. We have 4 places we need to move. 1, 2, 3, 4. And so those 2 spots then become zeros. So it's 4, 5, 6, 0, 0. If the exponent is negative, then you move it to the left to make it a smaller number. So here's our implied decimal spot. We need to move it 10 places to the left. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And all of those blank spots become zeros. So if the exponent is positive, then the original number will be greater. So that expanded form will be greater than 1. If the exponent is negative, then the original expanded number will be less than 1. It'll be a point something. So let's do some backwards. Let's change scientific notation into expanded form. So we have a positive 6, which means we need to make this number bigger. So we're going to move our decimal spot to the right. 1, 2, 3, 4, 5, 6. So 8, 6, 7. And then we have 1, 2, 3, 4 blank spots. Now notice we start where the decimal is. We don't just start adding 6 zeros to the end. You have to move the decimal. here it says 5.67 times 10 to the negative 1 meters per second. So since it's negative, we go left. And so we move left 1 spot. So that becomes 0.567 meters per second. 10 to the 2 watts. So here's our decimal spot. Go 1, 2 to the right since it's positive. That would be 280 watts. And then our last one, it's negative again. So we need to move to the left. 1, 2, 3, 4, 5. So now we have 4 blank spots. So after the decimal, we have 1, 2, 3, 4 zeros, and then the rest of our digits. Now, how does this really relate to what we're going to be doing with scientific notation in universal gravitation? Well, let's talk about how you would put it in your calculator. Most calculators will have a button that looks like this, or it'll look like EXP for exponent. Or if you have one of the standard TI calculators, above the comma button, it says EE. That's the same as this one. So this EE, it's not E, it's EE or EXP for your scientific notation. So let's say you wanted to put that 3 times 10 to the 8 meters per second in your calculator. You do not want to do this. 3 star 10 caret 8. You do not want to do this. If you do this, you could end up getting the wrong answer because your calculator will use the improper order of operations. So instead, you do 3, EE button, 8. The EE replaces the times 10 caret, so the times 10 to the. And this appears in the calculator as 3E8. Now, whenever you get an answer like this, do you have to put all of this down? Yes. You cannot have an answer of 3. 3 and 3 times 10 to the 8 are two completely different numbers. Again, think of money. $3 is not the same as 3 times 10 to the $8. So you have to put your exponent on the end.